Tonight, we are going to examine something buried deep within the geological record, an event from 56 million years ago that scientists still cannot fully explain. In a span that is brief by geological standards, the atmosphere absorbed thousands of gigatons of carbon. Temperatures rose, oceans shifted in chemistry, and ecosystems were forced into rapid adjustment. We refer to this interval as the Paleocene-Eocene Thermal Maximum, or PETM. It is not merely another ancient climate fluctuation. The scale of carbon released during this event exceeds the total output of modern industrial activity, and yet it unfolded long before humans existed. Now, let us pause and think carefully. When scientists study events this distant, they are not reading a written record. They are interpreting signals, chemical patterns preserved in rock. These signals function like a language, one that must be decoded with precision. Here is where the problem becomes interesting. The carbon released during the PETM carries a signature that closely resembles what we observe today when fossil fuels are burned. This similarity is not speculative. It is measured through isotope analysis, a reliable and widely used scientific method. So, we are left with a structured question. If the signature matches modern industrial emissions, but humans were not present, what produced it? In 2018, scientists Gavin Schmidt and Adam Frank approached this question from an unconventional angle. They asked whether an industrial civilization, if it existed millions of years ago, would leave behind any recognizable evidence. Their conclusion was precise and somewhat unsettling. Over millions of years, physical structures do not survive. Cities collapse, metals corrode, and tectonic processes recycle the surface. What remains are not artifacts, but chemical traces embedded in rock. This leads us to a critical observation. The PETM already contained such a trace, a rapid, large-scale carbon shift preserved in geological layers. At this stage, we are not claiming an extraordinary explanation. Instead, we are identifying a limitation. Science can detect patterns, but interpreting their origin is often far more difficult. To move forward, we must first understand a fundamental principle. Earth does not preserve history in the way we expect. It erases, reshapes, and compresses information over time. And that brings us to the next step in our investigation. How, exactly, does a planet erase its own past? To proceed, we need to adjust our sense of permanence. What appears stable within a human lifetime is, in geological terms, remarkably fragile. Consider a modern city. Concrete, steel, and glass give the impression of durability. Yet, if left unattended, these materials begin to degrade within decades. Vegetation breaks through surfaces, water corrodes structures, and foundations weaken. Extend this process to 10,000 years, and recognizable urban forms largely disappear. Now, extend further. Over 100,000 years, natural processes smooth out the remaining irregularities. Rivers shift course, sediments accumulate, and landscapes return to states that resemble their pre-human condition. At this point, even deliberate construction becomes difficult to distinguish from natural formations. A useful teaching insight here is this: geology does not record objects, it records changes. What matters is not what was built, but how the environment was altered. Over millions of years, the process becomes even more comprehensive. The outer layer of Earth is not static. Tectonic plates move, collide, and subduct. Ocean floors are continuously recycled into the mantle and replaced by new crust. Continental surfaces erode, uplift, and reshape in cycles that erase previous configurations. If our entire civilization were to vanish today, future geologists would not uncover intact machines or preserved architecture. Instead, they would encounter indirect evidence. This includes shifts in chemical composition, unusual concentrations of certain elements, and materials that do not typically occur in nature. For example, microscopic plastic particles would persist for some time, distributed through sediments. Certain industrial compounds would leave brief but detectable traces. Even radioactive isotopes from nuclear activity would appear as distinct markers. However, Each of these signals has a limited lifespan in geological terms. Eventually, most of these indicators fade, dilute, or are transformed by natural processes. Only one type of signal remains consistently visible across deep time: a rapid and significant increase in atmospheric carbon recorded in sedimentary layers. This is not a theoretical expectation. It is a pattern that geologists already recognize. And importantly, this exact pattern appears in the ancient record we are examining, so the question becomes more focused. If such a signal is the most durable trace of large-scale activity, what can it tell us about the event that produced it? To answer that, we must now examine the event itself in detail, beginning with its scale, speed, and impact on the Earth system. That signal, preserved across layers of rock, brings us directly to the event itself. To understand its significance, we must examine not only what happened, but how rapidly it unfolded. The Paleocene-Eocene Thermal Maximum represents one of the most abrupt climate disruptions identified in the geological record. Estimates indicate that between 3,000 and 7,000 gigatons of carbon entered the atmosphere over a period of only a few thousand years. On a human scale, this may appear gradual. On Earth's timescale, it is exceptionally fast. To make this clearer, consider a simple comparison. Geological processes such as mountain formation or continental drift typically occur over millions of years. In contrast, the PETM compressed a major atmospheric transformation into a fraction of that duration. It is the difference between a slow drift and a sudden shift. The consequences followed quickly. Global temperatures increased by approximately 5 to 8 degrees Celsius. This is not a minor fluctuation. Such a rise alters ocean circulation, atmospheric patterns, and the distribution of life itself. Oceans absorbed a significant portion of this carbon, leading to acidification. When carbon dioxide dissolves in seawater, it forms carbonic acid. This reduces the availability of carbonate ions, which many marine organisms rely on to build shells. As a result, large sections of marine ecosystems were disrupted. On land, species were forced to respond. Some migrated toward cooler regions. Others failed to adapt and disappeared from the record. What is important here is not only the scale of change, but the speed at which biological systems were required to adjust. A useful teaching observation is this: ecosystems are resilient, but only within certain limits. When environmental change exceeds the rate at which species can adapt, stability breaks down. Geologically speaking, the transition into this state of warming appears almost instantaneous. Sediment records show a sharp boundary, marking a clear shift from one stable climate regime to another. It is not gradual blending, but a distinct turning point. However, the most informative evidence does not come from temperature or extinction patterns alone. It comes from the composition of the carbon itself. The carbon released during this period carries a specific isotopic signature, one that points toward its origin. Understanding this signature is essential because it allows us to move beyond description and begin identifying possible causes. To interpret that evidence accurately, we must now look closely at how scientists read and analyze these chemical fingerprints embedded within the Earth's crust. To interpret that evidence accurately, we must now focus on the structure of carbon itself, because the key to this entire problem lies not in quantity alone, but in composition. Carbon, as an element, exists in multiple forms known as isotopes. The two most relevant for our discussion are carbon-12 and carbon-13. Chemically, they behave almost identically. However, they differ slightly in mass, and this difference allows scientists to track their origin with precision. Here is the important principle: living organisms do not treat these isotopes equally. Through biological processes such as photosynthesis, carbon-12 is preferentially absorbed. Over time, this creates a consistent pattern. Organic material becomes enriched in carbon-12 relative to carbon-13. This distinction is preserved even after organisms die and are transformed into fossil fuels. Coal, oil, and natural gas all carry this same isotopic bias. When these fuels are burned, they release carbon that is measurably richer in carbon-12. A useful teaching observation is this: isotope ratios function like a signature. They do not tell us everything, but they reliably indicate where a substance has come from. When scientists examine rock layers from the PETM, they observe a sharp shift in this ratio. There's a significant increase in carbon-12 relative to carbon-13. This shift is known as a carbon isotope excursion, and it signals a large-scale release of carbon derived from organic sources. What makes this particularly important is the pattern itself. The magnitude and direction of the shift closely resemble what we are currently measuring in the modern atmosphere due to fossil fuel combustion. This is not a matter of interpretation. The data is consistent across multiple locations and independent studies. The chemical signal is clear and reproducible. However, identifying the signature is only the first step. Interpreting its source is far more complex. If the carbon originated from organic reservoirs, then we must determine which reservoirs could release such a volume, and under what conditions this release could occur so rapidly. This is where the challenge emerges. Several natural mechanisms can produce carbon with this isotopic profile, but each comes with limitations when we consider the scale, timing, and global consistency of the PETM signal. So while the fingerprint is well established, the process that created it remains uncertain. To move forward, we must now examine the most widely accepted explanation and evaluate how well it accounts for the evidence. Among the proposed explanations, one stands out for both its plausibility and its limitations. It is known as the methane release hypothesis, and to evaluate it properly, we must begin with where methane is stored on Earth. Large quantities of methane exist beneath the ocean floor, trapped within structures called clathrates. These are crystalline formations where water molecules form a cage around methane gas, stabilizing it under conditions of low temperature and high pressure. In simple terms, methane is locked in an ice-like form within sediments. Now consider what happens if these conditions change. A slight increase in temperature or a reduction in pressure can destabilize these clathrates. When that occurs, methane is released into the ocean and eventually into the atmosphere. This matters because methane is an extremely effective greenhouse gas. Over short timescales, it traps significantly more heat than carbon dioxide. Even a relatively modest release can amplify warming. A useful teaching insight here is to think of methane as an accelerant. It does not need to be present in large concentrations to have a strong climatic effect. Its influence is disproportionate to its quantity. Based on this reasoning, scientists have proposed that a warming trigger could have initiated widespread methane release. This, in turn, would create a feedback loop. As methane enters the atmosphere, temperatures rise further, destabilizing more clathrates and releasing additional methane. At first glance, this mechanism appears to align with the rapid warming observed during the PETM. It explains both the speed and the intensity of the temperature increase. However, when we examine the details, several challenges emerge. First, the total volume of methane required is extremely large. The release would need to occur across vast regions of the ocean floor, and it would need to happen within a relatively narrow time window. Coordinating such a global event requires a triggering mechanism that is itself not fully understood. Second, and more importantly, the isotopic evidence does not align perfectly with pure methane. While methane does carry a carbon-12 signature, the pattern observed in PETM sediments suggests a mixture of carbon sources rather than a single dominant one. In other words, methane alone cannot fully account for the chemical signal we observe. This does not invalidate the hypothesis, but it does limit its explanatory power. It may represent part of the process, but not the entire mechanism. So we are left with a partial answer. A plausible pathway exists, but it does not resolve all aspects of the evidence. To move forward, we must now examine other proposed explanations and assess how well they account for the remaining gaps. Even with a plausible mechanism in place, the explanation remains incomplete. Methane may contribute to the observed pattern, but it does not fully resolve the discrepancies in timing, scale, and chemical composition. This is why scientists have explored additional hypotheses, each attempting to account for the missing pieces. One of the most frequently discussed alternatives involves large-scale volcanic activity. During the time of the PETM, a region known as the North Atlantic Igneous Province was highly active. Massive volumes of magma rose through the Earth's crust, forming extensive lava flows and releasing significant amounts of carbon dioxide into the atmosphere. At first glance, this seems like a viable source. Volcanic systems are capable of injecting carbon directly into the atmosphere, and they can influence global climate over long periods. However, the key issue here is not possibility, but rate. A useful teaching insight is this: in geology, the speed of a process is often as important as its magnitude. Volcanic emissions typically occur over hundreds of thousands to millions of years. The PETM signal, by contrast, indicates a much more rapid injection of carbon. To put this into perspective, imagine filling a reservoir. A slow, continuous flow will eventually reach a high level, but it produces a very different pattern compared to a sudden surge. The geological record of the PETM resembles a surge, not a gradual accumulation. Other explanations have also been proposed. Some researchers have suggested that a comet impact could have introduced large amounts of carbon into the system. Others have examined orbital variations, where subtle changes in Earth's position relative to the Sun alter climate patterns. However, each of these ideas encounters similar limitations. There is either insufficient physical evidence, or the proposed mechanism cannot generate the required volume of carbon within the observed time frame. What we observe, therefore, is a pattern repeated across multiple hypotheses. Each explanation aligns with certain aspects of the data, but fails to account for all of it simultaneously. This leads to an important conclusion. The PETM is not a mystery because we lack data. It is a mystery because the available explanations do not fully integrate the data we already have. In scientific terms, this is a problem of incomplete models rather than missing evidence. So we arrive at a point of uncertainty, but it is a structured uncertainty. We understand the signal. We understand many of the possible sources. What we do not yet understand is the precise mechanism that connects them. And despite this uncertainty about the cause, the consequences of the event are far more clearly established, and they provide essential insight into how Earth responds to rapid environmental change. Despite the uncertainty surrounding its origin, the consequences of this event are not ambiguous. The geological record provides a detailed account of how Earth's systems responded once the carbon entered the atmosphere. The most immediate effect was a substantial rise in global temperature. Estimates indicate an increase of approximately 5 to 8 degrees Celsius. To understand the significance of this, consider that even a change of 1 to 2 degrees in the modern climate system produces measurable impacts. A shift of this magnitude represents a fundamental reorganization of planetary conditions. One of the most striking outcomes was observed in high-latitude regions. Areas near the poles, which are typically cold, experience temperatures warm enough to support subtropical vegetation. Fossil evidence shows the presence of plant species that today would only survive in much warmer climates. This tells us something important. Climate zones are not fixed. They shift in response to changes in atmospheric composition, and when they do, entire ecosystems are forced to move or adapt. The oceans, however, reveal the most direct chemical response. As atmospheric carbon dioxide increased, a significant portion dissolved into seawater. This led to ocean acidification. When carbon dioxide reacts with water, it forms carbonic acid, which reduces the availability of carbonate ions. Many marine organisms rely on these ions to build shells and skeletal structures. When the supply decreases, their ability to survive is compromised. During the PETM, this process resulted in widespread disruption of marine life, particularly in deep-sea environments. A useful teaching insight is this: the ocean acts as both a buffer and a victim. It absorbs excess carbon, slowing atmospheric change, but in doing so, it alters its own chemistry. Deep-sea ecosystems were especially vulnerable. These environments are typically stable, with little variation over time. When rapid chemical change occurs, the species that inhabit these regions often lack the capacity to adapt quickly. The result was a significant level of extinction among deep-sea organisms. This is clearly recorded in sediment cores, where layers corresponding to the PETM show a marked reduction in biodiversity. Recovery, however, did not occur on human timescales. It required approximately 200,000 years for the Earth system to gradually return toward equilibrium. This recovery was driven by slow natural processes, including the weathering of rocks and the burial of carbon in sediments. This introduces an important principle. Earth has mechanisms to stabilize its climate, but these mechanisms operate over very long periods. So while the system eventually recovers, the duration of disruption is extensive. To understand the full impact of such a disturbance, we must now examine how living organisms responded under these conditions and why some survived while others did not. The environmental changes we have described did not affect all forms of life equally. Some species adapted, some migrated, and others failed to survive. To understand why, we must examine how biological systems respond under sustained pressure. In marine environments, the impact was immediate and severe, particularly in deep-sea ecosystems. These regions are typically stable, with minimal variation in temperature and chemistry. When rapid acidification and warming occurred, many species lacked the physiological flexibility to adjust. As a result, extinction rates among deep-sea organisms were significantly higher than in more dynamic environments. On land, the response followed a different pattern. Terrestrial ecosystems experienced shifts in vegetation, temperature, and water availability. In response, many animal species migrated toward regions that offered more favorable conditions. Migration in this context is not a random movement. It is a structured response driven by survival requirements, such as food, temperature, and habitat stability. However, migration alone does not resolve long-term challenges. Over time, species must adapt to new conditions at a biological level. This brings us to one of the more subtle but important patterns observed during the PETM: changes in body size. Fossil evidence indicates that several mammalian species became smaller during this period. This phenomenon, often referred to as dwarfism, is thought to be linked to higher temperatures and altered food quality. Smaller body sizes can be advantageous in warmer climates, as they allow for more efficient heat dissipation. A useful teaching insight is this: evolution does not aim for improvement in a general sense. It selects for traits that are advantageous under specific conditions. When the environment changes, the definition of advantage changes as well. Despite these adaptive responses, not all species were able to adjust quickly enough. Evolution operates across generations, and when environmental change occurs faster than genetic adaptation can keep pace, extinction becomes likely. This creates a clear pattern in the fossil record. Species that could migrate or adapt survived, often in altered forms. Species that could not respond within the required time frame disappeared. What is particularly important here is the rate of change. The faster the environment shifts, the narrower the window for adaptation. This observation has direct relevance beyond the PETM. It provides a framework for understanding how life responds to rapid environmental disruption. To fully appreciate the implications, we must now compare these past conditions with those emerging in the present, where similar pressures are developing, but at an even faster rate. The patterns we have examined in the past are not isolated to a distant geological interval. They provide a framework that allows us to interpret changes occurring in the present. At this moment, human activity is releasing carbon into the atmosphere at a rate that is comparable to, and in some estimates exceeds, the rates inferred for the PETM. Current emissions are on the order of 40 billion tons of carbon dioxide per year. This is not a gradual input, it is a sustained and accelerating process. To understand the scale, consider atmospheric concentration. Before the industrial period, carbon dioxide levels were approximately 280 parts per million. Today, that value has exceeded 420 parts per million. This change has occurred within a few centuries, which is exceptionally rapid in geological terms. A useful teaching insight is this: the rate of change often determines impact more strongly than the absolute value. Systems can adapt to high levels if change is slow. Rapid shifts, however, reduce the time available for adjustment. Climate models, which integrate physical laws governing atmosphere and ocean behavior, project a global temperature increase of approximately 3 to 4 degrees Celsius within this century if current trends continue. This range overlaps significantly with the temperature changes observed during the PETM. We are already observing early-stage consequences. Ice sheets are losing mass, contributing to rising sea levels. Ocean temperatures are increasing, altering circulation patterns and affecting marine ecosystems. On land, shifts in temperature and precipitation are influencing species distribution and agricultural stability. What distinguishes the present from the PETM is not the outcome, but the cause. In the case of the PETM, the trigger remains uncertain. In the present, the primary driver is well established. The combustion of fossil fuels releases carbon with a specific isotopic signature, and this signature is clearly detectable in the atmosphere. This provides a level of clarity that is unusual in Earth science. We are not inferring cause from incomplete evidence. We are directly observing the process as it occurs. The comparison, therefore, is not speculative. It is analytical. We have a past event that demonstrates how the Earth system responds to rapid carbon input, and we have a present situation that is producing a similar signal. The question that follows is not whether change will occur, but how extensive that change will be, and how long its effects will persist. To address that question, we must now return to the geological record, not to understand the cause, but to understand the long-term consequences that follow such a disruption. The comparison we have drawn is not intended as speculation. It is grounded in evidence preserved within the geological record. When we examine the PETM, we are not observing an isolated anomaly, but a clear demonstration of how Earth responds to rapid carbon release. The sequence is consistent. A large input of carbon enters the atmosphere. Global temperatures rise, ocean chemistry shifts, ecosystems destabilize. These are not independent events. They are interconnected responses within a complex system. A useful teaching insight is this: Earth's climate operates as a coupled system. Changes in one component, such as atmospheric composition, propagate through oceans, land, and biosphere. The effects accumulate rather than remain isolated. What is particularly important about the PETM is the duration of its recovery. Once the carbon was released, natural processes began to remove it from the atmosphere. These include the weathering of rocks, which consumes carbon dioxide, and the burial of organic material in sediments. However, these processes operate slowly. The return toward equilibrium required approximately 200,000 years. This timescale is critical. It demonstrates that while Earth can stabilize itself, it does so over intervals far longer than human history. This leads to a fundamental conclusion. Rapid changes in atmospheric carbon produce long-lasting consequences, even after the initial cause has ceased. In the present, we are generating a similar chemical signal. The increase in atmospheric carbon is measurable, and its isotopic composition confirms its origin. Unlike the PETM, this is not an inferred process. It is directly observed. This distinction changes the nature of the question we are asking. Previously, we examined the PETM to understand what might have happened. Now, we use it to understand what is likely to happen under similar conditions. The geological record does not provide predictions in the conventional sense. It provides analogues. It shows us how systems have behaved under comparable circumstances. And the pattern is consistent. Rapid carbon release leads to climate transformation, ecological disruption, and extended recovery periods. So the issue is no longer uncertainty about cause. The cause is known, the mechanism is understood, the outcomes are documented. The remaining question is not scientific but practical. Given that we can observe the process, measure its progression, and compare it to a well-documented event in Earth's history, the question becomes whether we will allow the pattern to continue or whether we will alter its course while there is still time to do so.